This is day 2 of integration by parts, and we're going to talk about the repeated use of integration by parts. So if you look at number 5, you can see that you can't integrate this normally. So we're going to use integration by parts, and we're going to let u, we need to figure out what u and dv are going to be. Okay, so u should be x squared and dv should be sine x. So we're going to work through it normally. We're going to say the derivative of x squared is going to be 2x, and the integral of sine x is negative cosine x. The issue that we run into is if we stopped at this point, if we put in our signs and our arrows, is we're not going to be able to find the integral of 2x, negative cosine of x. So I'm going to take it one more time. I'm going to repeat the use of integration by parts. So the derivative of 2x is 2. The integral of negative cosine x is negative sine x. At this point I can see that 2 and negative sine x, yes, I'd be able to integrate that. So the signs always go plus, minus, plus, minus, plus, minus. And you draw your arrows down until you get to a line where you can actually integrate. So at this point I'm going to go ahead and rewrite my work. I'm going to say this equals negative x squared cosine x minus, well actually a negative and negative is going to make it plus 2x sine x, and then minus, I'm going to put the 2 out front, the 2 and the negative out front, the integral of sine x dx. So it's going to equal negative x squared cosine x plus 2x sine x, and then the integral of sine x is actually negative cosine x, so it's going to change this to plus 2 cosine x plus c. Okay, so if you wanted to do a quick check to make sure your work was correct, we could do that by taking the derivative of the answer that we got. Okay, so if we take the derivative of this, we are going to get negative 2x cosine x plus x squared sine x plus 2 sine x plus 2x cosine x. Let's see, minus 2 sine x. So let's see if we can cross anything off. So our 2 sine x we can cross off, the 2x cosine x, and we are left with what was our original expression. Okay, so it looks like our answer is good to go. Alright, so let's look at another example. Now sometimes we set up a problem, we say, okay, you can see that u and dv here are going to be, and for simplicity's sake we will say we'll use u as e to the x and cosine x is dv, so the derivative of e to the x is e to the x. The integral of cosine x is sine x. Now again, we can't take the integral of e to the x sine x, we're still running into issues, so take the derivative again of e to the x, take the integral of sine x, I get negative cosine x, and we're like, well, that still is not going to work. We can see that this is going to keep being e to the x, and dv is going to alternate between sine and cosine x with alternating signs as well. So it's not going to really get to a point where we're ending where we can take the integral of it, but if you'll notice, e to the x cosine x is actually what our original integral was. So I'm going to go ahead and set this up, and you're going to see how I'm going to be able to combine like terms and still figure out what my answer should be. So plus, minus, plus, draw down your lines, draw across what your integral is going to be, and I'm going to rewrite this. So the integral of e to the x cosine x dx is going to equal e to the x sine x, let's see, and then it's going to be plus e to the x cosine x minus the integral of e to the x cosine x dx. Now, what I could do is I could combine my like terms together. So I could add 1 integral e to the x cosine x dx to both sides, and what's going to happen is I'm going to end up with 2 integrals of e to the x cosine x dx And what do you think we could do from here to get our integral by itself? Yep, you've got it. You want to divide both sides by 2 or multiply by a half. And since this was an indefinite integral, don't also forget your plus c at the end. Okay, if you wanted to check your work, you could take the derivative to see that that would work out. Something that's interesting with this is if you had changed what u and dv was, if you had u being cosine x and dv being e to the x, you could try it right now. What you're going to end up noticing is you're still going to end up getting the same answer. So exponential and trig, sometimes they can be interchanged for what u and dv are. All right, last problem, number 7. Sometimes when we look at problems, we call for a little bit of creativity when working through it. So this problem here, we see that we have secant cubed x, okay? We want to think about how could we split this up for u and dv so that we could very easily derive something and integrate something. We know we can pretty easily find the derivative of secant x. We know the integral is secant squared x, so I'm going to split it up in that form. I still have 3 secant x's. Alright, so the derivative of secant x we know is going to be secant x tan x. The integral secant squared x is just tan x. And maybe we're not quite sure secant x times tan x is going to work for integrating, but let's go ahead and plug it in and see what happens. And I'm going to go ahead and make this tan squared x. And I say, okay, I want to maybe try to get it all in terms of secant x. So I know that tan squared x is the same thing as saying secant squared x minus 1. So I'm going to substitute that in. And then I'm going to go ahead and distribute. And I'm going to split this up so it is secant cubed x, negative and negative is going to be plus just secant x. Alright, from here you should notice that you could combine like terms, so I'm going to put my secant cube x's together, so I have 2 of them. And the integral of secant x is actually the natural logarithm of secant x plus tan x. And then don't forget my plus c, and I just need to get my integral of secant cubed x by itself, so I'm going to divide both sides by 2. I'll just put 1/2 out front. Okay, and there is my answer. If you want to check it, you could find the derivative of it to make sure that it matches up with the original expression. The homework is below. It's going to be 8.2, day 2, page 531, numbers 14 through 34, every other even, 48 through 58.